Hello again. We're continuing on with our 2016 FRQ review. We're on question 3. And in question 3, I'm going to go ahead and highlight some information. We want to know the molar mass of an unknown metal, and that unknown metal is M. It's going to be reacting with my diatomic nonmetal iodine, and I do know that the metal is in excess. It's going to form the compound Mi2 as represented by the equation above. All of my I2 is consumed, so that is going to be my limiting reactant. And they've given us sort of a schematic of this step. So I start off, that's just the mass of my beaker. So that's going to be the mass of your beaker. We add the M2 and the mass goes up. We're going to add the I2, mass goes up again. So this is before the reaction. We're going to add water, reaction's going to occur. There's going to be some leftover M2, and then we're going to heat it up and dry off the water. So this is kind of good to look at to just sort of get an idea of how the steps of the chemical reaction are occurring. So then they give us some information in our data table. They give us the mass of the beaker. That was the first step. The mass of the beaker plus the metal. That was the second step. This is the mass of the beaker plus the metal plus the iodine. That's the third step. And these are the last steps. This is the mass of our compound after heating it up. So we look for a consistent, so no change in the mass to know that we've heated off all the water. Question A, I'm giving you A, B, and C initially so that we can look at to see where we're going, and then we'll go back and answer A, B, and C separately. They've told you that metal M is in excess. We want to calculate the number of moles of iodine that it was reacted. So we're going to go back to our data table for that. From there, we're going to calculate the molar mass of the unknown metal. And the student's hypothesizing it's ionic. So we're going to propose an experimental test that can support that hypothesis. So let's start with. So let's tackle question number A. I know that metal M is in excess. I want to know how many moles of iodine that reacted. So if you look up here on this data table, this mass right here is all three things, the beaker, the metal, and the iodide. This mass right here is everything excluding the iodide. So if I want to figure out the mass of the iodide, I'm going to take that higher mass, 127.570, and I'm going to subtract from it the mass of just the beaker and the metal, which is 126.549 grams. Both of those are grams. And when you do that, you should get 1.021 grams of your iodine. Okay? If I know the mass, I can figure out moles. I'm going to start with the mass, which is 1.021 grams. I'm going to divide it by my molar mass, which is 253.80. That's in 1 mole. And that gives you 0.004023 moles of iodine. Okay, and this is an important piece of information because if you go back to the reaction, 1 mole of your unknown metal is going to react with 1 mole of your diatomic iodine to give you that compound. Okay, so that is an important piece of information that we're going to need for the next part of this question. Okay, question B, they want us to calculate the molar mass of the unknown metal. And we know from the beginning that our unknown metal is iodine is our limiting, and our metal is going to be our excess. So we can't just take these two and subtract it, because not all of my metal is going to react. All right, but we do know how much iodine was formed, okay? And we do know the mass of our final compound. From our last problem, we figured out that the mass of iodine was 1.021 grams. We figured that out in the last problem. And we know that the mass of the final compound is 1.284. So if I subtract the mass of iodine from the mass of the compound, so 1.284 grams, and I subtract 1.021, that should give me the mass of my metal, which is 0.263 grams. So that gives me the mass of my metal. Okay, molar mass is the mass per mole. So we also need to know how many moles of the metal is. We don't know what the metal is, so we can't divide it by our molar mass. But we do know that the reaction is this. So we could figure out the molar relationship between the metal and the iodine. And the molar relationship is a 1-to-1. So I know how many moles of iodine I had. I figured that out in the last problem. The moles of iodine was equal to 0.004023. So that is also going to be equal to the moles of my metal. Okay? So to figure out my molar mass of my metal, I'm going to take my mass, which is 0.263, and divide it by how many moles are present, which is 0.004023. And when you do that, you get the molar mass of 65.4 grams per mole. All right. The student hypothesizes that the reaction is ionic, okay? And if you remember from the beginning, they talked about that this substance was water soluble. So there's a couple different things you could do to set up an experimental test. You could dissolve it and see if it conducts electricity. If it's ionic, it is an strong electrolyte, so it will conduct electricity. Okay. You could check the boiling point. If your boiling point is significantly high, that could also indicate that it is a ionic compound. So there's a couple different ways you could test for it. All right. These are the last two parts of the problem I couldn't fit. But they say that bromine, if I were to substitute bromine in for iodine, it will react with the metal more vigorously because bromine at its natural state is a liquid, whereas iodine is a solid. So D is they want to explain why iodine is a solid at room temperature when bromine is a liquid. And they give you some hints here. Always read that second part of the problem. They want you to say that your explanation clearly represents, the types and relative strengths of the intermolecular forces present in each of the substances. So we need to keep that in mind. Second part of the problem is they want to dispose of the unused iodine in a responsible manner. So to do that, they're going to convert it to its ion. This second part of the problem is not going to be a subject that's covered in the 2020 exam. We have not gone over it. but for E, I will talk about how you can do that. And F is write a balanced net ionic equation. That you will need to do, so we will go over that. So let's start with here I've got bromine and iodine. So let's talk about their intermolecular forces. They are both, nonpolar. Okay, so they both only have your LDFs. Okay, we do know that the size of your iodine molecule is going to be larger than your bromine molecule, which means it has more electrons. If it has more electrons, that means it has a greater ability to polarize. More electrons gives you a higher possibility or probability to polarize. So that means your LDFs for your iodine are going to be stronger. So your LDFs for iodine are going to be greater than your LDFs for bromine. Okay, which if your forces are stronger, that's going to indicate that you're going to be a solid, that this could be a more closely compact system than this. Whoops. Okay. Okay, question E is not going to be included on the 2020 exam, but I'm going to go over it. We haven't gotten to this just yet, but just for future purposes. The student wants to convert the iodine to a iodine anion, and they have access to 3 solutions and the standard reduction table below. So what we're looking for, they want to know which solutions should the student add to the iodine to reduce it to an iodine ion, and justify your answer, including a calculation of delta A. I'm not sorry, delta standard cell potential. So an electronic, or if we're looking at that, this is an oxidation. Again, these are reduction half reactions. Oxidation reduction reaction, always you have both happening at the same time, and you want those values to add up to the greatest positive value. Okay, so if these are the reduction reactions, and notice I have the reduction reaction for this compound, I don't have it for this, but this ion shows up on the product side of this half reaction. So if I were to flip this, so if I were to flip it, that would be the reduction reaction for that. So its value, its reduction value would be positive 0.08. Okay. These are reduction reactions. The oxidations are going to be the flip. So the oxidation reaction for this is going to give you an E0 of 0.08. This is the iodine, so we're not going to look at that right now. We do want this, we were trying to form this, so we're going to keep that as our reduction reaction. If we flip this, it's going to give us a negative 0.68. Okay, if we flip, this is for S2O3 2 minus, that's going to give us a negative 0.08. Okay, we want something that has the biggest positive, so you're going to add this number to all these numbers. If I add 0.54 to negative 0.08, my E0 is going to give me, let's 0.46. If I add 0.54 to negative 6.8, that's going to give me a negative value. So that's going to give me negative 0.14. Okay, and if I add this to that, that's going to give me, whoops, this should be a negative, sorry. So this should be a positive. If I add those two together, it's going to give me a 0.62. Okay, so that's my largest value, and that is for that ion. So I would choose that compound. All right, because it's going to give me the largest cell potential. That's a real slimmed down answer to that question, but it's not going to be covered, just to give you some background information. So the last thing we need to do is write the net ionic reaction for the solution that we just picked and the iodine. I know that the iodine is my reduction reaction, so I'm getting that half reaction from the table up above. And the idea is to cancel these electrons out. So I'm going to take that first equation and flip it, because I chose to use the solution with this ion. And when I flip it, I get, whoops. I get this half reaction. Okay, that cancels out my electrons for me. And so then I could just combine everything together, and I get the iodine reacting with 2s2O3, 2 minus, to give me 2 of my iodine ions, and S2O6, 2 minus. And that would be your net ionic reaction. Hopefully this helps. I will tackle question 4 next for you all. Thanks.